Hello everyone. Welcome to this extensive lecture series organized by Center for Computational Technologies, CCTech, Pune. This lecture is a part of the advanced course in multiphase flow modeling using commercial software Fluent. This particular lecture is an introduction to multiphase flow. Before we begin this lecture, let us have an overview of what exactly we are going to study. First, we will see what is phase. Then we will see single phase flows. Then we will know what is multiphase flow. Next is why exactly should we study multiphase flow. After that, we will see classification of multiphase flows. That is some basic classification or types into which multiphase flow is divided. Then we will see the various technical terminologies that are associated with multiphase flow. We should be aware of these terminologies whenever we begin to study multiphase flow. Then we will see a very short example of multiphase flow, that is bubble column reactor. Now, the first question that comes to our mind before we start studying multiphase flow is, what exactly do we mean by a phase? We know that thermodynamically phase is solid, liquid and gases. So, basically phase refers to states of matter which are generally classified as solid, liquid and gases. If we look around us, either in environment or in industry, we can see many types of flows naturally occurring or industrial phenomenon. Have you noticed any such industrial or natural flow phenomenon around you? Some of the pictures are shown here, like a droplet or a gaseous plume out of a chimney or cooling tower, the vapors rising out of a cup of tea. Can we judge whether these flows are single phase or multi-phase? Can we guess phases involved in these flows? Out of curiosity, you can just look around any natural or industrial phenomenon around you which involves flow or heat transfer or mass transfer. You would see that in reality, a lot of flows contain multi-phase. You should try to guess or study what type of phases are involved, the number of phases involved, how the exact phenomenon works. We will go into detail of this term called phase. Now, an obvious definition of phase is thermodynamic state, which is gas, liquid or solid, as we already discussed. But this is from thermodynamic point of view. We can define phase differently for computational purposes or for modeling purposes. It is possible to define different phases for computational purpose, although thermodynamic state is not different. We will see how this works exactly. Let us take an example of a dispersed gas. In this, solid flows with wide distribution of particle sizes. Now, in such cases, even though it's a single solid phase, we can usually define multiple phases representing the solid phase. That is, some particle size distribution in one phase and some bigger or smaller particle size distribution clubbed together as second phase. Sometimes it is also useful to treat two thermodynamically different phases as one phase for computational purpose. As an example, let us consider gas, liquid, solid, slurry reactor. This particular flow will contain three distinct phases, that is gas, liquid and solid. But solid is very minute and fine particles which generally follow the liquid. So they do not have the distinct flow or fluid velocity than that of the liquid. In such cases, for modeling point of view, it will be convenient to consider liquid and solid clubbed together as single phase, called as slurry. Thus, this particular complex three-phase system now is converted into a two-phase gas slurry system. So it is also important to notice whether the phases involved have their distinct velocity field or distinct velocity, which is different from any other phase. If that is the case, we can define them as different phases. If we see that one particular phase is following another phase and does not have its distinct velocity field, we can sometimes club them together and call it as a single phase. And now we have already studied how a single phase flow is modeled. It is modeled by using the Navier-Stokes equation, that is the continuity equation, the momentum equation, and the energy equation. As you know, the continuity equation is what looks like here. The momentum equation in three particular direction is as shown, that is x, y, z direction. This is the unsteady momentum equation, and the energy equation is as shown here. So when we model single phase flow, the basis forms the Navier-Stokes equation. This will also continue to be the basis for multiphase flow, as these are basic governing equation for any type of flow. The only difference or the additional point to be considered in multiphase flow is how we connect or interconnect the exchange between different phases. We will study this in detail as we go ahead in this particular advanced module. Now let us have a look at what is multiphase flow. Multiphase flow in simple terms is simultaneous flow of mixture of phases such as gases in liquid or liquid in gases and similar such flows. So when we say multiphase flow, what a picture should come to our mind is it is a mixture of different phases, and these phases have their distinct velocity field. Now as you are noticing, we are having a separate advanced module for multiphase flow. We are studying multiphase flow in detail one by one by covering each topic or terminologies associated with it. We would wonder, why do we need to study multiphase flow as a different branch or a different topic of study in CFD module? There are various reasons for it. We will see some of them here, some of the prominent ones. Multiphase flows are found in many industrial applications like chemical reactors and process flow industry. Almost all industrial flow contain multiphase flow. Natural and environmental flow phenomena like rivers and cloud formation involve multiphase flow. Just to see this in reality, try to observe how many flows that you see in nature or in industry are single phase flows. In reality, it is really difficult to isolate single phase isolated flow phenomenon. Thus, knowledge of multiphase flow physics is extremely important in order to carry any experimental or simulation study. Multiphase flow is a very vast field of study. It involves study of fluid mechanics, study of heat transfer or energy transfer, as well as mass transfer. In order to make things simpler, multiphase flows are generally classified into different types. These types are generally based on criteria like number of phases involved, the type of phases involved, the sizes of the phases involved, and as well as how the phases interact with each other. We will study each of these types in brief as we progress. Let us first have a look at dispersed phase flow. In such flows, one of the phases are in the form of discrete elements. But we do not see any connection between these individual discrete phase elements, which may be in the form of particles or droplets. Example of such type of flow is gas or bubbles in liquid. Next is separated flows. In such type of flow, two phases involved are separated by a distinct line of contact, which means that we can travel from one location to another in the same phase and remain in the same medium. An annular flow is an example of such type of flow. Annular flow will generally involve a liquid layer along the pipe and a gaseous inner core. So to summarize this slide, we will generally observe dispersed phase as a mixture of different sized droplets of particles dispersed around a continuous medium, whereas in separated flow we can distinctly divide one phase from another. Next type is gas liquid flow. As the name suggests, this will involve a gaseous phase and a liquid phase. They can be in different forms like bubbly flow and annular flow. Next is gas-solid flow. In such types of flow, we generally have gas with suspended solid particles. Granular flows are also among this, where particle-particle and particle-wall interactions are more important than forces due to interstitial gas. Next type is liquid-solid flow. In these types of flow, solid particles are carried by liquid. Another name for such flow is slurry flow. The solid particles will not have their distinct velocity field but will generally follow the liquid velocity field. Also, there are three-phase flow. Three-phase flow are also encountered in engineering problems. For example, bubbles in a slurry flow give rise to three phases flowing together. Three-phase flow is an emerging topic for research and computational modeling, and is a very advanced and interesting branch of study under multiphase flow. Now, as we have seen different type of multiphase flow, we will familiarize ourselves with fundamental terminologies which are used whenever we study any multiphase flow. Please try to remember these terminologies, as most of the advanced module will contain these terminologies frequently. First is the continuous phase or primary phase. By this we mean the carrier fluid, or generally the fluid which is present in bulk. Next is the dispersed phase or the secondary phase. This is the discrete phase which is usually in the form of particles or droplets or bubbles. This secondary phase may or may not have its distinct velocity field, which means it will sometimes follow the continuous phase, or it will sometimes have its own velocity field and affect the continuous phase flow. Next term is the volume fraction. It is defined as the ratio of the volume of the dispersed phase to the volume of the medium, that is the total volume. Mathematically, it is given by this particular equation. Now, unlike continuum, the volume fraction cannot be defined at a point, as it is defined based on volume. As the dispersed phase has its own volume fraction, the continuous phase also has its volume fraction, which is given as the ratio of the volume of the continuous phase to the volume of the entire medium, that is the total volume. Mathematically, it is defined by this particular limiting equation. You must have already guessed that the addition of these two, that is, the volume fraction of the dispersed phase and the volume fraction of the continuous phase, will come to be 1. Next are the density terms. Now, density or the bulk density is defined as the mass of the dispersed phase per unit volume of mixture, mathematically given by this limiting equation. Now, in this equation, delta md is the mass of the dispersed phase. This bulk density is related to material density by using the volume fraction of the dispersed phase. Also, the sum of the bulk densities for the dispersed and the continuous phase is the mixture density. So, in multiphase flow, we have two types of densities or two terminologies associated with density, that is the bulk density, which is the ratio of the dispersed phase per unit volume of mixture, and next is the material density, which can be obtained from the bulk density by using the volume fraction. So in multiphase flow, we generally have two terms for densities. One is the bulk density and the second is the material density. Material density is the classical defined density of any material. From that we can obtain the bulk density by just multiplying it by volume fraction. But always remember, bulk density is defined as the dispersed phase per unit volume. That is the mass of the dispersed phase per unit volume. Now we will move on to the next term, that is velocities. Now there are two velocities associated with multiphase flow. One is superficial velocity and next is the phase velocity. Now the superficial velocity is mass flow rate of a particular phase divided by the area of pipe in which that phase is flowing, or any other medium or geometry in which that phase is flowing. Now, superficial velocity is a term mainly associated with pipe flows. It is given by mass flow rate m of a particular phase divided by area A of the pipe and material density. So, in case of dispersed phase, this superficial velocity is given by this mathematical equation, that is mass of the dispersed phase divided by area of the pipe as well as the density, that is material density of the dispersed phase. Now, next term is the phase velocity. This is the actual velocity of the phase by which the phase material is flowing in that particular flow phenomenon. That is the velocity that we observe or measure. Now, again, volume fraction relates the phase velocities with the superficial velocity. If we multiply the phase velocities, actual velocities, by the volume fraction, we will get the superficial velocity. This term, that is the phase velocity, as well as this term, that is the bulk density. These two terms are generally defined for our convenience purpose for studying multiphase flow, and these are different from the actual velocity and the actual or material density of the phase, and they are usually obtained by multiplying the actual density and the actual velocity by the volume fraction. Next term is the mass concentration of the dispersed phase. Now, as you can see, this is the ratio of the mass of the dispersed phase to that of the continuous phase. It is obtained by simply dividing the bulk density of the dispersed phase by the bulk density of the continuous phase. Next term is quality. This term quality gives a measure or a feel of how much percent of dispersed phase is present in the medium. It is obtained by simply dividing the bulk density of the dispersed phase by the bulk density of mixture. Mixture meaning the bulk density of the mixture of continuous and the dispersed phase. Next term is phase loading. Now, this is the ratio of mass flux of the dispersed phase to that of the continuous phase. Do remember, this is defined as the ratio of mass flux, that is, it is obtained by material densities associated and not the bulk densities. Thus, we can obtain this by simply dividing the mass flux of the dispersed phase by the mass flux of the continuous phase. In the earlier part, we have already seen different type of flows. We are particularly studying these two distinct types in this because they contain some interaction related terms, that is interaction of one phase with other. So we have kept this distinction, that is dispersed phase, dispersed flow and dense flow classification in the latter part, rather than discussing this in the classification of multiphase flow. So let us see at dispersed flows. Now we already know in dispersed flow, the particle motion is mainly controlled by fluid forces like drag or lift. So in this, what we can say is the phase loading or of the dispersed phase is comparatively lower. That is, the presence of dispersed phase by mass is comparatively lower in this as compared to the continuous phase. So the bulk of the region is occupied by the continuous phase and it controls the entire flow phenomenon. Next is the other type we observe is dense flows. In dense flows, collision plays a major part in controlling particle motion. And as the name suggests, dense flows will particularly involve high phase loading of the dispersed phase. Under dense flows, also there are two particular types, that is collision dominated and contact dominated. Under collision dominated, collisions between the particle control the feature of the flows, whereas in contact dominated, particle motion is controlled by the continuous contact. Next is a very important terminology associated with multiphase flow, that is Stokes number. It is a non-dimensional number. It is defined as the ratio of particle relaxation time Td to the characteristic time scale of the flow, that is Tc. By particle we mean the dispersed phase. Now the particle relaxation time and the time scale of the flow are given by this particular ratio. Now, out of this mathematical formulation, what part you should take home is basically the significance of the Stokes number, which we will see now. So, if a very low Stokes number, that is particularly very less than 1, means the particles follow the continuous phase flow closely, Whereas a larger value of Stokes number, that is generally greater than 1, much greater than 1, means that the dispersed phase particles will move independently from the continuous phase flow. So what we should remember is, as Stokes flow increases, the independence of the dispersed phase increases. That is, the dispersed phase become more independent and start to have their own velocity field and move independent of the continuous phase flow. So now we will see some of the examples of multiphase flow, some of the industrial examples that are relevant. The first is the bubble column reactor. This is basically a reactor used for carrying out chemical reactions in industry, mainly gas liquid reactions. It is built of vertical columns of cylindrical form. So basically these are cylinders, vertical cylinders, and the gas is introduced in the form of bubbles from the bottom. This causes turbulence due to the motion of the gas stream, and it provides a kind of a Stirling action, or a kind of a rigorous turbulent mixing action for reactive gas exchange. And usually it consists of two phases, since there is liquid and the bubble stream, a very high turbulent bubble stream is introduced, which is containing gas. So it is a multi-phase system consisting of liquid and gas. This image show a plant equipment. This is a type of experimental representation of the bubbles which are introduced, a turbulent stream of bubbles from the bottom, as you can see here. So this causes a lot of turbulence and mixing, and it is used for enhancing the chemical reactions. And this is the CFD model. A CFD model, some contours of gas bubbles from a CFD model. These are the phase contours, as you can see here, a stream of bubbles. This is one of the example of a multi-phase system. The next is a gas liquid mixing vessel. Now, as you can see, you can guess from the image itself that this is basically a kind of a mixing vessel in which the mixing is carried out by rotation of the impeller type of blades. This is also used for chemical reactions and enhancing the chemical reaction by the rotating action or the mixing action of the rotary blades or impellers. This is a stirred tank reactor, and the impeller stir the reactions which leads to proper mixing of different phases. So most of the time it consists of two or more phases. These are the phase contours from a CFD models, and here also you can see the gas hold up contours. So this is also a common type of reactive or reactor vessel that is used, which mainly consists of multi-phase system, and multi-phase flow modeling is needed for this type of problem. Next is the fluidized bed. Now, fluidized bed are, as the name suggests, these are basically a type of solid and liquid mixture which acts as a fluid. So they are referred to as fluidized beds. These are basically beds for reactions. The purpose of such type of blades is that the mixture should behave as a fluid, that is, there should be mixing, but it gives the ability to promote more contact between the gases and the solids, which leads to more rigorous or more efficient reactions. In this, what is done is a pressurized fluid is introduced to a particulate medium. That is, the column, as we can see, consists of solid and a bed of solids, and a pressurized fluid is introduced from the bottom, which causes the whole bed of the fluid and the solid particles to behave as a fluid, and it causes mixing and reactions and high contact between the solid and the fluid. This is also a reactor, that is, it is used to carry out chemical reactions. This is the CFD model, which you can see. This is the bed of the solid particles, and you can see fluid introduced from the bottom. It goes up, there is mixing, there is high contact, reactions happening, and progressively the whole medium will behave as a fluid or liquid. So these are few of the examples that you will commonly see in chemical industry and which are commonly used for CFD modeling. And you can also study literature based on these systems, and you can go into depth into how multiphase flow is classified into these systems and how it is modeled. And you could, out of curiosity, you could know a lot of things about multiphase flow by just studying these three multiphase industrial systems. So to summarize this lecture, what you should take home from this particular lecture, that is the basic of multiphase flow, is that you should understand that thermodynamically there are three phases, that is solid, liquid, gases. But from modeling point of view or from industrial point of view, we have different phases.
we have different criteria for defining phases, and we may have a liquid-liquid system, but still we may treat it as two-phase system. Or on the contrary, we may have a liquid gas system, but we may treat it as a single phase system, depending upon whether they fit the criteria or not. So don't have a perspective of just a thermodynamic phase, like three phases of solid, liquid, gases, but learn to treat the entire flow as a entity, and then classify whether the flow is multiphase or single phase. Multiphase flow is simultaneous flow of mixture of phases, and multiphase flow are classified into different categories like separated flow, gas liquid flow, three phase flow, etc. You should be aware of the terminologies like volume fraction, phase density, mass fraction, phase loading, and Stokes number. You will be able to you will need them again and again when you model multiphase flow or study multiphase flow. So keep them in mind. Just understand what they mean and their significance. And as you already know from this lecture, multiphase flow is present in many environments. And if you are into chemical engineering or industrial mechanical engineering and you decide to go into CFD, it is certain that you will encounter multiphase flow modeling sometime in your career or study. So you need to have some basics of it. And I hope this lecture gave you a brief overview of basics of multiphase flow. And in the next lecture, we will see some important aspects of modeling multiphase flow, and then we will go into studying how to model multiphase flow. Before we end this, these are some of the references that were helpful for preparing this course content. So finally, thank you for going through this lecture, and if you have any feedbacks, you can always contact us, and see you in the next lecture. Thank you.